All right, so PreCalc Chapter 2, we're talking about polynomial power and rational functions. Again, we are breaking this into two parts, so we're going to stick with the polynomial ones for this first couple sections. Modeling and using linear and quadratic functions, modeling using power functions, modeling using polynomial functions of higher degrees. That will be the focus of the first part of our test. And then after that, we're going to look at how do we find zeros, complex zeros. How do we use that fundamental theorem of algebra, graphing rational functions, and then solving equations and inequalities that involve just a single variable. Okay, that'll be the second half of our chapter. For today, we are going to look at polynomial functions and linear functions, and average rate of change, and also linear correlation. Tomorrow, we'll hit the quadratic functions, and then Monday, how do we apply those quadratic functions? Okay, so my first question for you is, do you remember what a standard form polynomial function looks like? If I said write a polynomial, could you do that? Give me an example of a polynomial function. A function, so y equals x squared plus 2, okay? That is a quadratic function. It is a polynomial. You can create polynomial functions by stringing together different linear factors. So if I said, say, x plus 2, x minus 2, x plus 3. If I put all those together, multiplied it all out, I'd get a nice polynomial. All right, what do we get here? Okay, and if we FOIL that with the x plus 3, we get what? X squared times x. X cubed. Outsides? Insides. Last. Okay, so I could say f of x equals that. That is a cubic function. Okay? If I were to graph it, what shape does a cubic function have? Kind of that squiggle, that twist. Okay? And they can be more pronounced in the twist. When you start throwing all these other terms in here, you get the higher valleys and lower valleys, higher peaks kind of a thing. This has zeros at -2, +2, and -3, right? That's what would have made my function 0. So if I picture, well, this is going to be good. Okay, so if we were going to graph this, we would have zeros at -2, +2, and -3. And you said it was a twist, so it's going to start low, go up, hit your zeros. Yes? How do I know that it started low and twisted and ended high? Yeah. All right, so all that stuff that you learned last year in Algebra 2 about polynomials, it's going to come back. Okay, so what makes something a polynomial function? There are two criteria. Your exponent has to be a non-negative integer. Your exponent has to be a non-negative integer. That means it can be 0, 1, 2, 3, 4, 5, 6, 7, 8, etc. It just can't be a negative one. The other restriction is that your coefficients have to be real numbers. Okay? We do have something called a zero function where we're just saying y equals 0. It is still considered a polynomial function, but we refer to it as having no degree and no leading coefficient. in our polynomial, the first number here is our leading coefficient, and the highest exponent here is our degree. Okay, polynomial functions are defined and continuous on all real numbers. What does it mean for it to be continuous? Think about our graphs from the last few days. If it is continuous, it has no what? No what? No discontinuities. Okay, so there are no breaks, poles, vertical asymptotes, etc., right? You don't have any gaps in your graph. It is continuous. It is defined for all real numbers. Okay? No points of discontinuity. Is every relation a function? In other words, if I gave you any table of values, would it always be a function? What's our test for functions? Vertical line test. Does every graph, every set of points pass a vertical line test? No. All right, so looking at the four examples, we want to decide, first of all, is it a polynomial function? If it is, you're going to tell me the degree and the leading coefficient. If it's not, you're going to state why. Okay, so let's look at our first one. We had two criteria for it to be a polynomial. Your coefficients have to be real numbers. Your exponents have to be non-negative integers. Do we have that in A? Yes. Okay, so it is a polynomial. What is its degree? What is it? 3? Okay, highest power. And leading coefficient? Is that 4? Yep. It's the number in front of your highest powered piece. Okay. How about for B? Is B a polynomial? No, why not? What makes it, what? Negative exponent. Remember, a negative exponent just causes it to flip upside down? So this would really be the same as saying 6 over x to the 4th. Okay? And that has a discontinuity, right? X can't be 0, so it wouldn't be a polynomial function. How about for C? If the square root wasn't on top, then I would say yes, it's a polynomial. With the square root there, it's not. You cannot split the two terms here. Many students want to rewrite this as 3x squared plus 4x, right? And try to take the square root of each piece. You can't do that. So there is no way to change this C into this kind of expression. Okay? You can't get that square root out of there. So it is not a polynomial function. All right, so I just said you can't remove the square root to turn it into that polynomial format. How about D? Is D a polynomial? Yes? Okay, so what is its degree? Degree is 4, highest power is 4. What is its leading coefficient? -2, good. It's not in standard form. Usually we have the highest powered term first, but it is still a polynomial. All right, all constant functions as well as the zero function are polynomials. Now, we've talked, when I asked you for a polynomial, you guys gave me a quadratic one, okay, degree 2, quadratic polynomial function. Linear is our basic y equals mx plus b, has degree 1. Constant function, where a is not 0. So this would be something like saying just y equals 5. Okay? That is a horizontal line. We say it has degree 0. If we say y equals 0, that's referred to as the zero function. It does not have a degree. Okay? All right. We're going to look at cubic and higher powered polynomials in section 2.3. In this first section, we're focusing just on linear and quadratic ones. Today, it'll just be linear. All right. So we have a linear polynomial. A linear function is a polynomial function of degree 1 that has this format. Okay, that was what was in the table on the previous slide, where a and b are constants and a is not 0. If we replace the a with an m, it turns into our slope-intercept form. All right, so hopefully that looks familiar and you recognize those as linear functions. 2 questions. Are horizontal lines considered linear functions? Give me an equation for a horizontal line. Okay. So y equals 2. Is that mx plus b? Look back at your chart that we just had. Right? Y equals 2 is a constant function. It's not a linear function. Okay? Linear functions have degree 1. That does not have degree 1. That has degree 0. Is a vertical line a linear function? Is it a function at all? No. So if we're talking about linear functions, they can't be vertical lines. They can't be horizontal lines. All right? Vertical is not a function at all. Horizontal is a constant function. So when we refer to something as a linear function, it will be one of our slanted lines. Another term for that is oblique. Okay? So linear functions will be your slanted lines. All right. Example 2, we are going to find a linear function that fits the criteria that f of negative 1 is 2 and f of 3 is negative 2. What are they giving you here? Points. They're giving you 2 ordered pairs. They are saying that if we put negative 1 in, we get a 2 out. And if we put a 3 in, we get a negative 2 out. So if you know 2 ordered pairs, how do you find the line? Yeah, find the slope first, and then use slope in one of your points to write your equation. Okay, so what is our slope going to be? Which ones go on top? The y's. All right, does it matter if I do 2 minus negative 2 or negative 2 minus positive 2? Once I pick an order, though, I have to do the x's in the same order. So if I do 2 minus a negative 2, I'm going to have to put negative 1 minus 3 on the bottom, which gets me 4 divided by negative 4, or a slope of negative 1. Okay? Then I can use either point. Let's say we use the first one. How do I come up with the equation? Given a slope, given a point. Point slope form. All right, y minus 2 equals all right, so it's y minus y1 equals m times x minus x1. All right, simplifying, y minus 2 equals negative 1x minus 1. And adding the 2 over, we get negative x plus 1. Okay? Would that be a slanted line? Yes. Describe it for me. Starts at 1, has a slope of, so down 1 over 1. Okay? So it is a linear function. So we verified it graphically. Confirming it numerically would just mean check your points. Do they work in the equation? So if I put in the negative 1 for x, do we get 2 out? Yes. If I put in a 3 for x, do we get negative 2 out? All right, so it fits the points that I had. We've got the right line. All right, there's a lot of stuff about slope on this page. You guys are used to seeing it y2 minus y1 over x2 minus x1. Okay, that's the same thing they're giving you right here. It's just instead of x's and y's, they're saying I'm going to have an a and a b, and then I'm going to have my y value at a and b. Okay? So the average rate of change for our function f of x between a and b is given by that formula. Again, it's the same thing you've been working with. Okay? Typically, we think of average rate of change as our slope. Now, we can have a rate of change for other things. A parabola has different rates of change depending on which points along the parabola that you're using. Okay? So if we had a parabola, your rate of change between those 2 points is going to be much steeper than, say, your rate of change between those 2 points. Okay? And when you get into calculus, you'll start looking at more of that piece. For us, we're talking about lines today where slope and average rate of change are interchangeable terms. All right, so a constant rate of change. It says a function defined on all real numbers is a linear function if and only if it has a constant, non-zero average rate of change between any 2 points on its graph. So that slope has to be the same regardless of what points you pick. Okay, constant and non-zero. Because remember, if the slope is 0, you have a horizontal line. That's a constant function, not a linear function. So we are saying that for a linear function, average rate of change is just the same as rate of change, because it's always the same. And that's our slope. All right, our example. It says Camelot Apartments bought a $50,000 building, and for tax purposes, they are depreciating it $2,000 per year over a 25-year time span. What is the rate of change for the value of the building? It says we start at $50,000 and they're depreciating it $2,000 every year. What does depreciating mean? You're losing value. It's going down. So what would the rate of change be? Negative 2,000. We're losing $2,000 every year. So how would we write an equation? V of t, we want the value of the building as a linear function of the time. T would be years. So V of t would equal what? Close. Negative 2,000 t plus 50,000. Yep. Now it says evaluate V of 0. Well, if you put a 0 in for time, what do you get? We just bought it, right? Time 0. We just bought the building, and it had a value of $50,000. When we find V of 16, we are saying, what is the value 16 years later? So put a 16 in there. $2,000 times 16 would be $32,000. So negative $32,000 plus $50,000 would be $18,000. So after 16 years, the value of the building is down to $18,000. The fourth question says, solve V of t equaling 39,000. In other words, what time, after how many years, would that value be down to 39,000? Okay, so we're not putting it in for t, we're putting it in for y. What's 39,000 minus 50,000? Okay. Negative 11,000 divided by negative 2,000. 11 divided by 2 is 5.5. So after 5.5 years, the value would be down to 39,000. Okay, we're just basing it on a linear function. All right, some notation again. The rate of change of a linear function is the signed ratio, meaning it has a positive or negative sign to it. It's the ratio of the corresponding lines rise over run. So you've heard of the term rate of change, slope. We use an m for that. We've talked about it being rise over run. The change in y over change in x. Have you seen this notation? That's referred to as delta y over delta x. Just means change in y over change in x. It's a shorthand notation. All right, so based on that apartment building, at time 0 we had a value of $50,000. 1 year later, it was down to $48,000. Our change in x was 1. Our change in y was negative 2,000. So the change in y over change in x comes out to be negative 2,000. And that is constant. It's going to keep going down $2,000 for every year we go up. All right. F of 0, we just found that with the apartment building. We found V of 0. We said that was $50,000. So the initial value, F of 0, that's your starting amount. Okay? In terms of a linear equation, this would be the B term, right? In our apartment building one, we had y equals negative 2,000 x plus 50,000. Okay, so it would be this, starting value, initial value. It's your y-intercept. The constant term for any polynomial function is the function's initial value. That means I can come up with a huge polynomial. If all of these x's get turned into zeros, all of this stuff disappears. So when you put a 0 in, all you have left is your constant term. Okay? So initial value for any function is that constant term, which is going to be the y-intercept of your graph. All right, so to summarize what we've been talking about with linear functions, we have a polynomial of degree 1 It fits that y equals mx plus b kind of format. It has to be a slanted line with a slope of m and an intercept of b, a y-intercept of b. It has a constant non-zero slope. Our graph is going to be increasing if our slope is positive, decreasing if our slope is negative. And b is our initial value. Okay? All right. The last piece, we're going to try to calculate a linear regression line. All right? And we're going to use that to figure out the correlation, how strong, how weak it is. Okay? We've given you some pictures. This one is referred to as a strong positive linear correlation. This one is a weak positive. When we talk about strong and weak, we are referring to how well the line fits the data. How close do those points line up? When we talk about the positive or the negative, we've got some negative ones over here. When we talk about positive versus negative, we are referring to the slope. Okay? So because these dots are moving up, we would have a positive slope, so it's a positive correlation. The points in this first picture are much closer to that line than the points in the second picture. Okay, so strong versus weak. These both have a negative slope, so we would say they have a negative correlation. Again, this one would be strong and this one would be weak. If you have a picture like this middle one, where I say draw a line from those points, you'd say where would it be? I can't tell. All right, they're just randomly all over the place. So we would say there's little or no correlation. All right, so we want to make sure that your calculator is going to have that R value when we do our linear regression. So grab your calculators and go to Catalog. Catalog should be right above your 0 key. You want to go into Catalog and then scroll down to Diagnostics On and hit Enter twice. A lot of times the default mode is to have them off. So if you've had your calculator cleared for maybe a standardized test or something, it can change that. So I just want to make sure everybody has theirs on. So go into Catalog, Diagnostics On, hit Enter twice. It's right above the 0 key. All right, we good with that? Did everybody get it to say done? Okay, so it's turned them on. All right, so our correlation constant. All right, our R value, that correlation coefficient, is a number that measures the strength and the direction of your data. Okay, your R value is always going to be something between -1 and +1. If R is +1 or -1, it means that every single point of your data lines up on that line. It's a perfect fit. Okay? Positive means you have a positive slope. -1 would mean a perfect fit, but a negative sloping line. If your R value is something positive, but maybe not all the way to 1, then you have a positive linear correlation, and the closer you get to 1, the stronger it is. If R is negative, we have a negative linear correlation, and again, the closer you get to -1, the stronger it is. If R is 0, we say there's relatively no correlation. Okay? So an R value of, say, 0.2, I would say is very, very weak. An R value of 0.9 is going to be very strong. Okay? All right, it says good modeling practice demands that we have a theoretical reason for selecting a model. If I say come up with a regression equation, you have to know, why am I picking a linear one, or why am I picking a quadratic one? All right, what in the problem is telling me that's the type of function I want to use? When we talk about fixed costs, for example, a business has fixed costs. Maybe it's the rent of the building, all right? Every month they're going to pay the same amount for the rental. Okay, that's a fixed cost. It is constant. You're just saying cost equals $3,000 a month. Okay, that's fixed. Demand, if you think of supply and demand, demand is a product, or demand for a product is a function of its price. So as the price changes, the demand is going to change. It's going to be a slanted line. All right, so we can use a linear function for that. So our last example here is going to be a linear function. Take a minute. We're going to put these in as list 1 and these in as list 2. All right, so I'm just going to pause the recording and give you time to do that. Okay, it says Twin Pixie makes donut-shaped oat breakfast cereal. They sell 15-ounce boxes at various prices over a period of time. So looking at our data here, our lowest price is $2.40. Our highest price is $3.60. When we had a low price, we could sell about 38,000 boxes. As we raised the price to $3.60, we could only sell about 18,000. Okay? So as the price increases, people aren't as willing to buy it. It says, use the data in the table to write a linear model for demand in boxes sold per week as a function of the price. That's why we put price in L1 as our x's, and we had boxes sold as our y value. We want to come up with that linear model and then describe the strength and direction of the correlation and use it to predict what the sales prices, or how many sales we can make if the price is dropped to $2 or raised to $4. So how do we come up with the linear regression? What keys do we hit? Stat, calc. I think it's number 4, right? Linear regression. All right, go ahead and do that. Stat, calc number 4. All right, remember, you want to store the equation. So on the newer calculators, go where it says store equation. You're going to do variables, y variables, and then function and y1. What that's going to do is after it calculates it, it's going to dump it into your y equals screen as your first equation. Okay, so store, go to variables, y variables, function, and y1. Okay, the equation that we're coming up with, y equals negative 15,358.929 x plus 73,622.5. What did it give us for an R value? What does your calculator say for R? Negative 0.981? Okay, so that would tell me it has a very strong negative correlation. We've got a negative sign here, and this is very close to 1. So strong negative correlation. All right, and we can check that. go ahead and graph it. Let's set our window between 2 and 4 for X because our prices were somewhere between $2 and $4. And boxes sold, let's go from 10,000 to 40,000. Okay, go ahead and graph it. All right, your dots are very close to a line, aren't they? Okay, so it is strong and it's going in a negative direction. Now they asked us to find when the price was $2, how many boxes can we sell? And when the price is raised to $4, how many boxes can we sell? We can get that information right from our table because it's already dumped our equation in there. So if you go to your table, go to where X is 2, and what do you get for Y? I get 42,905. Agree? Now, we also could have put a 2 into our equation here for our X value and calculated it that way. Okay? When the price is raised to $4, we can sell 12,187 boxes. Okay? All right. Your assignment. It's questions 1 through 18, 47 through 49, and 51. I did put a hint on here. For questions 13 through 18, your Y scale is not necessarily a 1. So watch that kind of carefully.